seen that m of j omega is equals to c of j omega divided by r of j omega, and this is for a feedback system, feedback control system. Okay, so the maximum value of this, so if you plot this, if you plot the magnitude of this the log magnitude plot for this m of omega, then the peak or the maximum value of this m of j omega, m of omega, that is known as the peak resonance. And this peak resonance, this occurs at a frequency which is known as the resonant frequency. Okay, so that resonant frequency is given by omega r. Now, what is the significance of this peak resonance? Okay, so this peak resonance, basically it is an indication of the relative stability of the system. So you can say that if your system has a larger peak resonance, so that means that it corresponding to a larger peak resonance in the frequency domain, that corresponds to a larger peak in the step response in the time domain. So, and we know that if we have a larger peak overshoot, then the relative stability of the system that reduces. Okay, so in that way we can relate, or we can correlate the peak resonance in the frequency domain with the with the maximum peak overshoot which we were seeing in the step response in the time domain analysis. Okay, so generally the optimum value of MR, MR, the peak resonance, that is kept in between 1.1 to 1.5. Then this is the resonant frequency. So the frequency at which this resonant peak occurs, that is known as the resonant frequency. Then we have something which is known as the bandwidth of the system. Okay, so ideally, yesterday when we were talking about, ideally we would want that the bandwidth of your system, or if this is your m omega, so the magnitude, so this is, let's say, in dB, and this is the omega. Okay, so ideally we would want that the magnitude of this m omega, or the magnification of the system, should be constant for all frequencies. Okay, at least even if not for all frequencies, at least for a certain range of the frequencies in which we are working. Okay, but in the whenever you do a practical in a practical scenario, this kind of an ideal, this kind of a flat gain is not possible. So what will happen is that we will get a gain, or the magnitude of this m omega, it follows a path like this. Okay, so here in this case, so how do we determine the bandwidth of a system? So bandwidth of a system is defined as the frequency at which the amplitude of m omega drops to 70.7% of its zero frequency level. Okay, so at the zero frequency the value was 1. Okay, so ideally it should have been 1 throughout, but in practical scenario it is not 1. So the value at which, or the frequency at which the value of this m omega, that is dropping to 70.7% of its zero frequency level, that is 0.707, since the zero frequency magnitude is known as bandwidth. And 0.707, if you take 20 log dB, log 0.707, that is equals to 3 dB. So in the log magnitude scale, you can say that the frequency at which the log magnitude curve falls below or reaches 3 dB below the zero frequency gain, that is known as the bandwidth of a system. And the significance of the bandwidth is that it governs it is important for analysis of the noise filtering, or for analyzing the noise characteristics of a system, whether the system will be able to filter out the noise, the unwanted noise signals which are present in your system. That depends on the bandwidth of the system. And also this bandwidth, it is a measure of the transient response properties of the system. So that means if you have a larger bandwidth, so in the frequency domain, if you see that your system has a larger bandwidth, that signifies that the rise time in the time domain analysis, that will be faster. So a larger bandwidth, it signifies a faster rise time in the time domain analysis. And a smaller bandwidth, in case of a smaller bandwidth, so it means that only the low frequency signals will be allowed to pass, and all the high frequency signals, there will be a significant amount of attenuation for the high frequency signals, right? So if you see this figure, so if you have a lower, the bandwidth is low, so that means that, so whatever frequency is there from 0 to omega b, these frequencies will only be passed with a with a moderate amplification factor. But beyond omega b, the amplification is reducing drastically. So that means the signals will not be passed on to the output in a very authentic way. So there will be a significant attenuation of the high frequency signals. Okay. If you have lower bandwidth, so that means that only very small or very low frequency signals will be passed, and as a result, the response of your system would be very slow and it would be very sluggish, you can say. Now then there is another factor which is known as cutoff rate. Okay, so sometimes, so this bandwidth, as we have already told, that bandwidth is basically defined in order to cancel out or to reduce the effects of the noise signals which are present in your system. So sometimes what happens is that only if you have the information about bandwidth, that is not sufficient to distinguish between what is your actual wanted desired signal and the unwanted noise signals. So in that case, we have to specify another thing which is known as the cutoff rate of the frequency response at high frequencies. Okay, so this if you have a steep cutoff characteristics, so and if that steep cutoff characteristics is accompanied by a large value of the resonant peak, that means that the system will have a very low stability margin. So that means that the relative stability of your system will be much lower. So the cutoff frequency is basically the frequency at which m omega it reaches 0.707 of its zero frequency value. So this cutoff frequency and the bandwidth, this omega, these two are same, but the rate at which the slope of this curve m omega at the high frequency range, or how the slope of m omega is changing at the value of omega b, that signifies what is the cutoff rate. And if you have a very steep cutoff characteristics along with a very large value of the resonant peak, then you can say that the overall system stability reduces in that. So now let's try to find out what would be the values of this resonant peak, resonant frequency and bandwidth of a second order system. Okay. So the moment you are given with a second order system, so you can write that the transfer function of the second order system would be in a generic form. It will be expressed like this, right? Omega n squared divided by j omega squared plus 2 zeta omega n into j omega plus omega n squared, right? Because we have omega n squared divided by s squared plus 2 zeta omega n s plus omega n squared. So this is usually Cs by Rs for a second order system. So we are simply substituting s by j omega and we are getting this equation. So now if you want to find out the resonant frequency, so the resonant frequency means the frequency at which the value of the magnitude of mj omega will be maximum. So what we'll do is that we'll take the derivative of this and we'll equate it to 0, and from there we will solve for the value of omega. And after solving that, you will get that the value of omega r is equals to omega n square root of 1 minus 2 zeta square. Okay, so now this value of omega r, it has to be a real value because the frequency at which we are working, that has to be a real frequency. So this value will be real only if the value of 1 minus 2 zeta square, that is greater than equals to 0. Okay, so that means the value of zeta should be less than equals to 0.707. And at this value of omega n, if you substitute this value of omega in this equation, you will find out what would be the magnitude of the resonant peak. So that magnitude is given by 1 by 2 zeta square root of 1 minus 2 zeta square. So as long as the value of zeta is lying between 0 and 0.707, we are getting a resonant peak. But the moment zeta is more than 0.707, what happens is that this resonant peak, this vanishes and the value of this resonant peak becomes equals to 1. So there is effectively, you can say that there is no resonant peak. Okay, so that is the expression for the resonant peak and the resonant frequency. Then we have already defined the bandwidth. So bandwidth is basically the frequency at which the amplitude or the magnitude of m omega, it drops to 70.7% of its zero frequency level. That means 3 dB below the zero frequency gain. So how we can find out the value of this bandwidth? So that means that the value of that m omega will be equals to 0.707. So we will simply solve this equation for 0.707, and we will get what would be the value of u. And we have in the previous case, we have actually defined the value of u to be omega by omega n. So once you have found out the value of u, you can find out what would be the value of omega. So bandwidth would be omega n under root of this expression, right? And if you plot the value of this resonant, so this is resonant peak. So if you plot the value of this resonant peak with respect to damping ratio, you see that when the damping ratio is 0.707, it is monotonically decreasing till 0.707, and after that it is becoming equals to 1. And when the value of zeta is equals to 0 at that point of time, that means that when the system is an undamped system, at that point of time the peak or the resonant frequency, that is an infinite value. Yes, someone, does anyone have any doubt? Okay. So at 0, the value, if the value of zeta is equals to 0, at that point of time the value of MR is going to be infinite. So now if we want to correlate the frequency response and the time response characteristics of a second order system, so we can say that the value of MP, that is the peak overshoot, and the value of this resonant frequency, they are both dependent on the value of zeta only. Okay, and when you have, and for zeta less than 0.707, the peak overshoot, that is MP of the unit step response in time domain, and the resonant peak for the closed loop frequency response, that is MR, they are correlated. Correlated means you can have a correlation, you can write the correlation between the value of the peak overshoot and the value of the resonant peak. Okay, but beyond zeta equals to 0.707, since the value of MR doesn't exist, so there is no correlation as such. Similarly, if you want to see the value of the damped frequency of oscillation, that is omega d, and the resonant frequency, so the damped value of omega d is given by omega n square root of 1 minus zeta square, right? So this is in the time domain. And in the frequency domain, omega r is given by omega n square root of 1 minus 2 zeta square, right? So if you just divide these two, you will say that the omega r and omega d, these two are also related. And if you plot this ratio omega r by omega n, so this would be omega r by omega n, and if you plot it with respect to zeta, you will see it will follow a curve like this, and this curve will exist till the value of zeta is 0.70. And also from the bandwidth perspective, so the bandwidth is in the frequency domain, that is indicative of the undamped natural frequency of oscillation, that is omega n, for a given value of zeta. So that means we can say that the bandwidth is governing what would be, or it is indicating what would be the speed of the response in the time domain for a given system. So if the rise time in your time domain is, since the rise time is increasing with the value of zeta, so we can, and the bandwidth is decreasing for decreasing with increasing value of zeta and a particular value of omega n. So there comes a relationship between the rise time, that is the speed of the response, and the bandwidth. So they are, you can say that these are inversely proportional, or they are inversely correlated. If you increase the value of zeta, then bandwidth decreases, but at the same time the rise time increases. The system becomes much faster in response, but the bandwidth of the system reduces, that is at the cost of reduced stability of the system. Okay, and we can also say that the bandwidth is directly proportional to the value of omega n, because here we have seen that, see, the bandwidth is equals to omega n multiplied by this factor. So bandwidth is directly proportional to the undamped natural frequency of oscillation of the system. And also this, if you have a higher bandwidth, that corresponds to a larger value of the peak overshoot that is present in case of the step response of a second order system. Okay, so these are the different frequency response characteristics of or the frequency response specifications that are usually specified whenever we are dealing, or whenever we are analyzing a system in the frequency domain. Okay, so Now we'll talk about something which is the stability of the system, how we can analyze whether a system will be stable or how stable or the relative stability of the system using Bode plot. Okay, so the first thing is that, so let us say that this is how your Bode plot looks like. So you have certain, so this is the magnitude plot and this is the phase plot. Okay, so we first of all we will identify two frequencies. Okay, so the first frequency is known as the phase crossover frequency or omega PC. Okay, so what is this phase crossover frequency? So it is known as the frequency at which the phase angle first reaches minus 180 degree. So let's say for this curve, the phase angle is reaching the value of 180 degree at this point. Okay, so this will be my phase crossover frequency. And the other frequency that we want is the gain crossover frequency. And the gain crossover frequency is basically the frequency at which the magnitude of the open loop transfer function is unity, or the magnitude, or you can say that the log or the frequency at which the gain of the system is equals to 0. Okay, so that means that, so here you see that it is crossing the, this is the gain crossover frequency, right? So, and the gain margin is defined as the maximum value of the gain of a control system that a control system can have to operate in a stable state. So that means that if we find out what is the value of the gain margin, so the gain margin of the system, the gain of the system at the phase crossover frequency is known as the gain margin. So this is the phase crossover frequency, and corresponding to this frequency we see that the gain of the system is 20 dB. Okay, so that means that the gain margin of the system will be 0 minus the gain at the phase crossover frequency, that is 0 minus 20 dB. So the significance of this 20 dB is that if you change the value of the gain of your overall gain of your system such that the magnitude, the log magnitude is varying, can be varied till minus 20 dB. Till that point the system will be stable, and if you change the gain of the system such that it crosses the gain margin, then the system will become unstable. Okay, and for calculation of the phase margin, so this is the gain crossover frequency. So the gain crossover frequency is the frequency at which the system or the magnitude plot is crossing the 0 dB line. So this is the gain crossover frequency, and the corresponding to this gain crossover frequency, we will see what is the phase angle at that frequency. Okay, so phase margin is basically defined as the amount of phase lag that have to be added or that can be added to the gain crossover frequency in order to bring the system from a stable system to an unstable system. So we can play around with a phase margin of only 180. So the phase margin is defined as 180 degree plus the phase angle at gain crossover frequency. So we can play around with this much of a phase margin in the overall Bode plot in order to keep the system in the stable region. If you make a gain margin, so here let's say again this phase margin is equals to minus 9 degree. So if it is going, so we have a formula, or we will see that how we can analyze whether, depending on what is the phase margin and the gain margin, whether your system will be stable or not. Okay, so if you have, so the criteria goes like this: if both the gain margin and the phase margin, they are positive, that means that the phase crossover frequency is greater than the gain crossover frequency, then we say that the system is stable. Okay, and the system will be marginally stable if both the gain margin and the phase margins are 0, or the phase crossover frequency is equal to the gain crossover frequency. So if GM and PM has to be positive, or the phase crossover frequency has to be greater than the gain crossover frequency. But if both GM is equals to PM is equals to 0, and this gain crossover frequency is equals to phase crossover frequency, that is the condition for a marginally stable system. Now if either of GM or both, either or both of GM and PM are negative, or this omega of gain crossover frequency is greater than the phase crossover frequency, then we say that the system is unstable. So once you have drawn, or once a Bode plot is given to you, you have to find out what is the value of the gain crossover frequency, the phase crossover frequency, and the corresponding gain margin and phase margin. So depending on the values of this gain margin, phase margin, gain crossover frequency and phase crossover frequency, we can find out what would be the how much stable your system would be. Okay, so this was about how we can analyze the stability of a system using gain margin or using Bode plot. Okay, so another application for using frequency response plot or the Bode plot is that it is very the information, since in case of frequency response we are only interested in the steady state response of the system. Okay, so the steady state response of the system means that we need to find out what would be the steady state error of the control system. Ideally, we would want that the steady state error of the control system should be equals to 0. That means my output should always follow my input very accurately. So how do we find out how do we find out the information about the steady state error of a control system? So let's say that if you have a unity feedback control system. So in case of an unity feedback control system, if you remember that we have earlier we have talked about some static error constants, right? Steady state error constants where which were like the position error constant given by Kp. Then we had velocity error constant Kb. So this was Kp. The velocity error constant was given by Kv and the acceleration error constant was given by Ka. Okay, so these velocity or these error constants, they basically describe the low frequency behavior of different systems. Okay, so basically if you have Kp, so Kp will govern, or it will describe the low frequency behavior of a type 0 system. So type 0 system means that there are no poles at origin. Type 1 system means there is a single pole at origin. Type 2 system means we have two poles at the origin. Okay, so using this static, or so vice versa, you can say that if you know the Bode plot, so if you analyze the low frequency behavior in the Bode plot, so from there you can find out what would be the values of Kp, Kv and Ka. And once you know the values of Kp, Kv and Ka, you can find out what would be the static or the steady state error constants. Okay. So for a given system, only one of these three static error constants is finite, and that is the significant value. And all the other static error constants, they will be either 0 or infinite depending on the type of the system that you are dealing with. So you can say that the type of a system, it basically determines the slope of the log magnitude curve at low frequencies. And once we can, so from that slope, once we find out the value of Kp, Kv and Ka, so from there we can find out information about the steady state error of the control system. Okay, so now let's take a type 0 system. So this is an example of a type 0 system. So this would be J omega. Okay, so G of J omega. So this is a type 0 system because we don't have any poles at origin. Okay, so if you want to find out, so if you remember the position error constant Kp was found out by limit s tends to 0 Gs, so that would be equals to K, right? So this is nothing but K by 1 plus St1 into 1 plus St2. So this is Gs. Gs is equals to this. Okay, so the value of the position error constant is nothing but K. Okay, and if you draw this is again J omega. So if you draw the low frequency asymptote, or if you draw the log magnitude curve for this response, so you see that there are two corner frequency. So one corner frequency is at 1 by T1 and the other corner frequency is at 1 by T2. So there are two poles and there is again Kp, right? So if you draw so there are like three components. So this is one factor number 1. This is factor number 2 and this is factor number 3. So we will have three asymptotes. We'll combine all the three asymptotes and we'll find out what is the overall Bode plot of the system. Okay, so if you draw this, so for this Kp, so we will have a zero frequency. So Kp means we'll have a horizontal line till of the magnitude 20 log Kp. right? So we have a horizontal line over here. Then what we'll do is that we'll first encounter this pole that is at 1 by T1. Okay, so this is the first corner frequency, 1 by T1. Okay, so at this corner frequency we have a pole, so that means we will have a slope, we will have a change in slope, we will have a straight line asymptote with a slope of minus 20 dB per decade. So we will have a slope of minus 20 dB per decade. And for this one, if you remember that before or for value of omega less than 1 by T1, the asymptote is equals to 0 dB, and for greater than 1 by T1 it is a minus 20 dB per decade straight line. So this is this one. So then at 1 by T2 at the other corner frequency, so at the other corner frequency we again have another pole. So for this one also, the till 0 to 1 by T2 the component or the contribution is 0. So this part will remain same, this will be unchanged. But beyond 1 by T2 what will happen is that we will add one more minus 20 dB per decade straight line will be added. So that means that the slope will change and it will become minus 40 dB per decade. Okay, so then by seeing the Bode plot you can identify whether what is the type of the system. So here, since the low frequency is a horizontal straight line, so we can say that with a magnitude of 20 log Kp, so we can say that this is a type 0 system, and depending on this value you can find out what is the value of Kp. From the Bode plot you can find out what would be the value at this point, and that would be nothing but 20 log Kp. If you equate those two, you can find out the value of Kp. And once you know the value of Kp, if you remember for a step input and a type 0, if you have a type 0 system and if you provide a step input to that type 0 system, then the steady state error is given by 1 by 1 plus Kp. So we can find out the value of Kp from here, and we can find out what would be the steady state error constant, steady state error for this kind of a system. Okay. Then let's talk about a type 1 system. So a type 1 system means the transfer function will be given by k by j omega, that is a single pole at origin. Okay, so and the velocity error constant is given by kv is equals to s into gs, so that is equals to k. So we can rewrite the value of g of j omega as kv by j omega. Now if you draw the Bode plot for this k by j omega, so that means it will have two components. One, so this is factor number 1 and this is factor number 2. So for this one, you will have a straight line at 20 log k. Okay, so if this is omega and this is in dB, so you will have a straight line, the magnitude of the straight line will be 20 log k. And for this j omega, what you will have is that we will have a slope straight line with a slope like this. So the slope will be minus 20 dB per decade, and it will cross the 0 dB point. So let's say if this is 0 dB at omega equals to 1. Okay, at omega equals to 1 it will cross the 0 dB line. So the overall Bode plot for this k by j omega will be nothing but addition of this plot and this plot. Okay, so the addition of these two means what? That this straight line asymptote will be nothing but will be shifted by a value of 20 log k, right? So that means we can say that at omega equals to 1, previously it was crossing 0 dB line, but now at omega equals to 1 it will cross this value 20 log k. So now we can, so if you draw this line, so the initial slope of the straight line will be minus 20 dB per decade. Okay, so minus 20 dB per decade, it is coming like this. So basically you will have, so this g of j omega at omega equals to omega 1. Let's say that this straight line, so this is not the, so for this system actually the plot looks like this. It will be something like this. Okay, so this is omega, this is in dB, this is your minus 20 dB per decade line. Okay, so and if this is the value of omega, let's say this is omega 1 and this is 0 dB. Okay, so this value of omega 1 or the value at which the straight line is crossing the 0 dB line, that if that frequency is known as omega 1, so we can find out from this what will be the value of omega 1. So omega 1 will be nothing but, so g j omega will be equals to 0 dB. So g j omega is kV by j omega at omega equals to omega 1, that is equals to 0 dB, and from there you can write that the value of kV is equals to omega 1. So if you can find out what is the value of this omega 1, the frequency at which this 0 dB, this minus 20 dB per decade line is crossing the 0 dB straight line, that will give you the value of the velocity error constant. Okay, and this velocity error constant, so for a type 1 system, the steady state error is given by 1 by kV, right? So now if you have a system, if you have a unity feedback system, let's say that it's given by k by s into js plus f. So here you have, this is this component number 1, you have a pole over here, pole at origin, and this is your component number 3. Okay, so for this first two factors, you will have a straight line which is going like this, which is nothing but this plot. Okay, and at this corner frequency, that is the value of, at this corner frequency, there will be a change in slope because we have a first order pole at that position. So that means there will be an addition of minus 20 dB per decade slope will be added. So it will become a minus 40 dB per decade line. Okay, so from here you can write that if you can rearrange this equation, so gs will be equals to nothing but k dash by s into ts plus 1. Okay, so if you equate these two, you will see that the value of k dash is equals to k by f and t is equals to j by f. So that means that the corner frequency, this omega 2, this corner frequency is equals to 1 by t, is equals to 1 by t, which is equals to f by j. Okay, so now the value of kV, so, and let's say that the intersection point of omega equals to 1, this point, the value of, so this is, if this is, let's say this is omega equals to 1. Okay, so the value at omega equals to 1 is nothing but 20 log k in this case. So previously at omega equals to 1, if the factor was only j omega, then at omega equals to 1 it was crossing 0 dB, but now since we are adding these two, so that means at omega equals to 1 the value will be equals to 20 log k. So if you expand or if you extend this straight line, so it is crossing the 0 dB line at omega 1, omega 2 is the corner frequency, and omega 3 is the frequency at which the second asymptote, that is the minus 40 dB line, is actually crossing the 0 dB straight line, and the omega equals to 1. So the magnitude at omega equals to 1 is for the first initial slope, if you keep on extending this one, so that will be given by 20 log kV. Right, so you can find out the value of kV. kV will be equals to limit s tends to 0 s into gs, and from this equation you can write kV is equals to k by f. Okay, so similarly, as I have already told, this omega 3 is basically the intersection of the 0 dB of the minus 40 dB line with the 0 dB straight line. Okay, so omega 2 is known to us, omega 1 is already known to us, so we want to find out what is the value of omega 3. Okay, so for omega 3, what we will have is, we will simply write the transfer function, or we will write the magnitude. So 20 log of the given transfer function will be equals to, at omega equals to omega 3 will be equals to 0 dB. So right, so this is the, since this is the overall, this is the Bode plot of the overall system. So that means at omega equals to omega 3, the overall system is having a gain of 0 dB. So we will find out what is the value of omega 3. Omega 3 is given by k by j. And if you simply rewrite these equations, so omega 2 and this is kV, kV is nothing but omega 1. So if you see those things, so you will see that omega 1 multiplied by omega 2 is equals to omega 3 square. So as we know that on a logarithmic plot, the difference between, so the difference between the logarithm of two magnitudes will be equal. So this is a ratio, so that means log of omega 1 minus log of omega 3 will be equals to log of omega 3 minus log of omega 2, right? So we can say that omega 3 is basically lying in the midway between omega 1 and omega 2. Now if you compare the open loop transfer function of the given system with the with the standard system. So the standard open loop transfer function of a second order system is given by omega n square s into s plus 2 zeta omega n, right? So if you compare the given transfer function with this one, you can find out the value of zeta, and you see that the value of zeta is equals to nothing but omega 2 by 2 twice omega 3. So that means if you can identify the values of omega 1, omega 2 and omega 3 from the Bode plot, you can find out what would be the value of the velocity error constant, what will be the value of the zeta. All these things you would be able to calculate from the Bode plot. Similarly, if you have a type 2 system, so in a type 2 system, what will have, you will have two poles at the origin. So the function will be k by j omega whole square. Okay, so if you write the value of Ka, so Ka will be a square into Gs, which will be nothing but equals to K, right? So we can rewrite the value of Gj omega as Ka by j omega whole square. Now let's say if you have the Bode plot of a sec type 2 system is given by this one, so that means you can say that the initial slope, so since there are now two poles at the origin, so that means the initial slope that we will have, that will be, so there are two components now. So this is component number 1 and this is component number 2. Okay, so for this j omega square, so what we'll have is that we'll have a straight line slope, and the slope will be equals to minus 40 dB per decade. Because if you remember that if whenever we were talking about that multiple poles at a certain location, so that means at that case the slope of the straight line will be equals to minus 20 n dB per decade, where n is basically the number of poles, or number of, in this case, number of poles at that particular position. So here the value of n is equals to 2. So that means the slope of the initial slope will be minus 40 dB per decade. And this will have, and if this is omega equals to, let's say if this is omega equals to 1, so that means at omega equals to 1, the magnitude will be equals to 20 log Ka, right? So this would be the polar plot, this would be the Bode plot for, or the log magnitude plot for this given transfer function. Okay, so now let's say that we have another transfer function which is, or the another Bode plot which is given by this. Okay, so from this one you can identify that there are like multiple corner frequencies. Okay, so there is, yes, anyone is speaking? Okay, so that means here you can identify the value. So there is this one corner frequency over here, there is another corner frequency over here, and another corner frequency over here. So at this point there is a change in slope, at this point again there is another change in slope, and at this point we will have another change in slope. So that means depending on how your slope is changing, so let's say here it's given that the initial slope was minus 40 dB per decade. At this point the slope changes to minus 60 dB per decade. So that means at this corner frequency we will have a pole, right? We will have a first order pole. That's why we will have another minus 20 dB per decade, and the overall system will be minus 40 dB per decade. Then after, at this corner frequency, if this is, let's say, omega 1 and this is omega 2, this is omega 3. Okay, so at omega 1, we have a first order pole, right? At omega 2, you see that previously the slope was minus 60 dB per decade, but after omega 2 the slope becomes minus 20 dB per decade. So that means we can write that the overall change in slope is plus 40 dB per decade, right? So plus 40 dB per decade, it can be either due to two first order, it can be due to two first order zeros at that position, or a single first order, or a pair of complex conjugate pair of first order complex conjugate pair of 0. Okay, and again at this point there is another change in slope, and depending on, since this is not given, this is probably minus 40 dB per decade. So that means at omega 3 again you will have another pole, a first order pole. So now for this system, how do we find out what is the value of Ka? Because from the Bode plot we want to find out what, since we want information about the steady state error of the system, so we have to find out the steady state error constants. So we have to find out what is the value of Ka. right? So value of Ka is, so if you extend the initial the initial asymptote or the first asymptote, if you extend it and it reaches the value of 0 dB at, let's say, omega equals to a, omega equals to omega a, so that means the first asymptote was because of the contribution of K by j omega whole square, right? So that means you can say that for K, if you want to find out the value of this one at omega equals to omega a, so that would be equals to 0, and the value of omega a will be equals to square root of Ka. Okay, so if you can find out what is the value of omega a, you can find out what is the static acceleration error constant, and from there you have idea about what is the steady state error constant or the steady state error in your system to a parabolic input. So that means that from here we see that if we observe the low frequency component of the Bode plot, that means the initial slopes of the straight line asymptotes which are present in the low frequency. So if we analyze them, if we find out at what frequency they are actually crossing the 0 dB line, from that position we can find out what would be the value of the corresponding static error constants, and once we find out those static error constants, we can find out what is the steady state error. So that is how you can calculate you can use Bode plot in order to calculate the steady state error from the steady state error of a given system. So do you have any doubts in how to construct this Bode plot and how this analysis is being done? So any doubts till now? Okay, since no one is responding, I'm guessing it's all clear to you. So next what we'll do is that we'll talk about another type of plot or another type of representation of the frequency response of a system, that is given by something which is known as polar plot. So basically, what is a polar plot? Okay, so the main disadvantage of Bode plot, you can say that you have to have two separate plots. Okay, so there is one plot which shows the variation in the gain or the overall magnitude of the gain with respect to frequency, and the second plot shows the variation in the phase shift with respect to frequency. So whenever you are drawing a Bode diagram, so you have to have two plots. Okay. So polar plot, what it does is that it takes information from both the plots and it plots a single graph. Okay, so that means we can say that in a polar plot, basically the polar plot of a sinusoidal transfer function, if that sinusoidal transfer function is given by g of j omega. So this is a plot of the magnitude, that is magnitude of g of j omega versus the phase angle g of j omega on the polar coordinates, and as we are varying the value of omega from 0 to infinity. So in the previous case when we were drawing Bode diagram, so the x-axis of the Bode plot was frequency. Okay. In this case, in case of a polar plot, what we do is that we plot the magnitude of so the y-axis is basically the magnitude of the, or you can say the real part of this gj omega, and in the x-axis we have the imaginary component for, or rather, sorry, I said it in the opposite way. So what we plot is that the magnitude of gj omega versus the angle of gj omega. Okay. So since we know that this sinusoidal transfer function, this is a complex quantity, so we can expand it and we can write it in form of some real quantity plus j into the imaginary part. Okay, and it can also be written as magnitude angle of that corresponding g of j omega, and it is like, we can represent this as m angle phi, where m is basically the magnitude of g of j omega, right, and phi is equals to the angle of g of j omega. Okay, so from this plot you can see that gj omega in a phasor plot or in a polar plot will be represented by a phasor with a magnitude of m and the phase angle of phi, and this phase angle is obviously measured as positive. If it is measured in the counterclockwise direction, then we say that the phase angle is positive. So as if we vary the value of omega from 0 to infinity, so since these two are functions of omega, so that means this value of m and phi, these two will also change. Okay, so the moment the value of m and phi are changing, so we can say that the phasor, so let's say if your phasor is something like this, the magnitude being, so the magnitude and angle being this. So as we keep on changing the value of the value of omega, so this phasor will follow a different path. Okay, so this phasor, maybe it will go over here, maybe it will go over here, it will go till this side. So depending on the value of omega, this phasor will trace a path. Okay, so the tip of the phasor, it traces a locus in the complex plane, and that locus is basically known as the polar. Okay, so then the next thing that we have is the is what is known as a Nyquist plot. So Nyquist plot and polar plot are basically the same things, but the only difference being that in case of Nyquist plot, we are varying the value of omega from minus infinity to plus infinity. But the significance of Nyquist plot, that why we need to vary omega from minus infinity to plus infinity, and the significance of it in terms of stability, that we'll discuss later on. But for now, we can just say that the Nyquist plot is equivalent to a polar plot, and in case of polar plot, we are changing the value of omega from 0 to infinity, and in case of a Nyquist plot, we are changing the value of omega from minus infinity to plus infinity. Now, this information about this negative frequency is basically redundant, because anyways, the magnitude and the real parts of g of j omega, they are basically even functions of omega. Okay, and the phase and the imaginary part, they are odd functions of omega. So if you know the polar plot, or if you know the plot for omega equals to 0 to infinity, you can simply reverse it, and you can find out, or you can draw the plot for omega varying from minus infinity to 0. So effectively, we need to calculate only, or we need to draw only the plot for varying omega equals to 0 to infinity, and we can, from there only, we can deduce what will be the nature of the response for omega equals to minus infinity to 0. Okay, so now basically this polar plot, it can be used. So in case of Bode diagram, what we saw is that from the Bode plot, we had to find out what is the value of gain margin, phase margin, and from there we can analyze the stability of the system. Okay, but from polar plot, you see that if this is a polar plot, so you have a real axis, so the x-axis is the real axis, and the y-axis is the imaginary axis, and this is, let's say, a polar plot. Okay, so this polar plot can also be used to determine the closed loop stability of a system similarly by determining the gain margin and the phase margin. So here, since we have a single plot which combines both the information from both the log magnitude plot and the phase plot for the Bode diagram. So here what we have, that we can say that we are actually dealing with only we have to plot only a single graph, and from there we can find out what would be the values of the or what would be the value of the gain margin, phase margin, and subsequently analyze the loop stability. But there are certain limitations of using polar plot also. Okay, so just by seeing a polar plot, it doesn't indicate the individual contribution or the contribution of the individual factors that are present in the open loop transfer function. So in case of a Bode plot, we saw that given the different individual components, so if your open loop transfer function has like multiple factors, like maybe a pole or zero at origin, maybe some first order factor, some second order factor. So what is the effect of those factors in the frequency response, that can be obtained from the Bode diagram, but the same that kind of information cannot be obtained when we are plotting a polar plot. Okay, and also if you in case of Bode plot, if you add a pole or a zero to your system, let's say that if you add a pole or zero to your system, then you can simply modify the Bode plot just by identifying the corner frequency at which the pole and the zero is added, and then going into and drawing the frequency response. But in case of polar plot, if you have to see the effect of addition of poles and zeros, you have to recalculate the overall expressions from the scratch, and then you have to draw the polar plot. So in a nutshell, you can say that the calculation of the frequency response or drawing the frequency response or the polar plot, that is little bit tedious compared to the Bode plot. Okay, so I'll stop here today. In tomorrow's class, we'll talk more about this polar plot. Do you have any doubts till now? Any doubts? Okay, so that's all from my side today. So we'll conclude the class now, and we will again meet tomorrow. Thank you, everyone.